I just wanted to kind of cover what they were talking about at the end, because it took me like years to understand what they were saying. So for the rest of you in the room who didn't understand how to black start a machine, because I was always confused by this. I don't know exactly how to draw this, but basically you've got a turbine spinning a shaft, you've got a synchronous machine hooked up to it, and what Dimitri was saying is they're taking the AC waveform coming right out of the terminal of the machine, running it through some rectifier, like this, and then feeding it back into the field of the synchronous machine. So the question is, how do you start it? Because you need this to run this, but you can't get this until this is already running. So I have no idea. I always imagine them rolling out some giant battery, but maybe it's sitting there all the time. But you have to have some way to provide the field current just to get it started, and that's what they were talking about at the end. So is it in the, are there batteries always there, or?
My experience is 20 years out of date.
Okay.
When I was doing repairs for General Electric, they have the big hydro unit, and then they'd have a rotating DC generator sitting on top on the same shaft.
Okay. So
and then sometimes they'd have a real little one.
So everyone would have one that would usually not run. It's just there
Well,
when they
it
needed to
depends
start.
on the unit. They were
Yeah.
rapidly changing most of that out for
Okay.
static exciters.
Yeah.
I assume some of them still exist where they could just bootstrap themselves up.
The batteries are sized, after the rundown, after certain many hours, they can still flash the field.
Okay.
That's what they have a big battery.
To get it started. Okay. I would always imagine like a cart or something. Anyway. There's a whole nother group of engineers somewhere who worries about all this stuff. That's what's
Again, we do have, if I remember, in some of our projects, some permanent magnet station service units that.
okay. They had some permanent, just enough to get spinning with no load.
Like at the Dalles, I think actually, we've got a couple there on one of the lower decks that we could walk by a number of times.
Okay. All right, so we have covered all of this stuff in lots of detail. Actually, we haven't done stabilizers yet. Tom will have a talk on that tomorrow. I think last time I taught this course with him at Texas A&M, that's the first time I understood stabilizers. So I get the feeling Tom had figured it out the week before. So it's like you only understand it when you suddenly have to teach it. But it's a good presentation. Anyway, what I'm going to talk about now is loads and how do we model loads in power systems. I would say that the 1920s to 1950s was sort of the great era of figuring out how to model synchronous machines. I think we are in the middle of the great era and kind of wandering around not really knowing what to do right now, but we're trying. So that's where we're at with loads. So, all right, traditionally loads, I kind of divided into two camps. One is we're just going to treat it as purely algebraic functions of voltage and frequency. I'm going to go through those in a moment. And then the next is actually try to model the device, like model the induction motor, model the power electronics, have some dynamic model that represents it. The simplest model is to treat everything as a constant impedance, because then you just throw it in the Y bus with the transmission line stuff and you're good to go. But this doesn't really make any sense as far as what is in reality. So there are literally hundreds and hundreds of papers. A lot of them you can blame Dimitri for on load modeling and kind of the work that a lot of it's coming out of Lawrence Berkeley. There's a guy named Joe Edo there who's been shepherding government funding to fund other labs and professors to kind of look at how loads are modeled. But the most common approach, if you were in the Eastern Interconnect, this is still what they do mostly. They're starting to actually put in other kinds of dynamic models, but really up until 5 years ago, this was it. They would take every load and they just come up with a set of coefficients that say it says the load is a function of the voltage, and maybe they would say it's a function of a constant power. It's some constant times voltage. So if it's linearly dependent on voltage, that means it's a constant current. And then they do the square of voltage, which means it's a constant impedance. Or maybe they were really motivated and they did lots of data collecting and curve fitting and came up with a polynomial where they had different coefficients. So they could say that it's 2.5 and 3.2 and 1.2 for the coefficients instead of 0, 1, and 2. But ultimately, this is just saying it's a function of voltage. It's not a lot different than the power flow. In the power flow, you can do this, though most of the time people just do constant powers. So, just peek at simulator just to remind you. If you had a load in the power flow, we have a constant power, constant current, and constant impedance. All right, the vast majority of people in the power flow world never set these to anything other than 0. But you could. All right, other kinds of loads they would model with these just functions of voltage is something like lighting. Actually, this is a good picture down here. What this is showing, this is reactive power, this is real power, and this is tests done in 1999 and in 2012. And right here, the blue line shows what an electronic fluorescent light looked like in 1999. You can see at some voltage the power would start going up, and then it would drop as it goes. In 2012, it changed into this. Does anybody know what changed between then? It's not LEDs. No, this is before LEDs. It's just the power electronics. Instead of having the old electronic ballasts, they switched over to power electronic ballasts that just have a power electronic control system that's, if you look at it, it says as long as the voltage is above 0.77, you get full power. As soon as it drops below there, it all goes away. And then if you look at the reactive power, it became wildly different. And what's going on is as the voltage drops, the power electronics is having to consume more and more and more bars in order to keep the power constant. And then at some point it just gives up and shuts off. But wow, that's completely different over a 13-year period. So keeping up with the technology down on the consumer side is difficult. I would suspect we tend to be 5 to 10 years behind. It's like we finally figure out how it worked, but we figured out how it used to work all the time. This is just a plot out of a paper showing different coefficients for different kinds of bulbs or different kinds of power. This is kind of old. This is the old discharge lighting where it has this power to 4.5. If you look, that's essentially modeling this. This is like a very high exponent on reactive power. So I think we probably came up with this model in the late 1990s, and then by the time we started implementing it, it really wasn't useful anymore because the electronic ballast changed. The other thing you can add is add some frequency dependence. So if you're in a wet case, there's a model called WSCC. This WSCC model, let's show a block diagram here. This is essentially what I'm showing. You've got the power is a function of voltage, and then there's a frequency dependence term right here. The terms are different, but it's the same concept. So here we're saying there's a function of frequency. Typically, This frequency dependence is, let me just think this through, is positive, so that when the frequency goes up, the load tends to go up, actually, which is good. It means the load is providing some damping, because if the frequency goes up, it's good that the load is following it up, because it'll tend to bring the frequency back down. But all of this isn't really modeling the devices. All of this is just taking a bunch of data that you have and trying to fit how the load behaves versus the measurements you have. You're not actually modeling the devices. Yep.
Jake, yeah, other than large loads, can you actually model devices? Because usually you just get like a feeder load. It's a
Well, correct.
composite. It's a composite of
Exactly,
log
and that's
or
where we're
whatever.
going to go. Yeah.
Okay.
It's like how do you model a group of things, and that's what the composite model gets us to. Correct. Yeah, it's hard. It's way easier with the generator.
Mhm.
All you have to have is money to pay staff or a consultant to go do a test. But how do you figure out how 1 million homes behave?
Pretty much.
Well, even then, it's constantly changing,
Yeah.
and the technology keeps changing. It's much more difficult. One other comment, we're not going to talk a ton about it, but frequency, I'll talk about that in the section later today. All right, so what kind of models can we actually model the devices? The simplest one that we can model the actual device, well, I guess the simplest one would be an electric heater, which is just a big resistor. But the simplest dynamic model would be an induction motor. So induction motors were a big part of what caused AC power to be useful back in the late 1800s. Let me just skip through some of this. I don't want to cover all of it. So the basic model of an induction motor, if you derive it in an undergrad course, you kind of get to something that looks like this. If you look at it, it kind of looks like a transformer, where you've got a series winding, this winding, and then a magnetizing impedance. And actually, we're not going to go through all the math on this like I did with the synchronous machine, but the idea is it's kind of like a spinning transformer. So it's like the synchronous machine. The difference is that the field winding is actually just shorted out, so there is no field voltage. And this tends to but this represents the steady state behavior of a synchronous machine. And we're not great with the nomenclature here in power systems because we're using the term S right here, which is different than the S in all the other diagrams we do here. This is not the Laplace transform, like the Laplace operator like we had in the block diagrams. This is what is called slip. All right, slip is kind of a key definition on a induction machine. And it's basically the normalized difference in the speed of the rotor compared to the frequency of the electric signal. So induction motors will always spin slower than the frequency of the electric system. It's like they're trying to catch up, essentially, the whole time. So if the system's at 1 per unit frequency, an induction motor will be at 0.9 something at steady state. It's always a little bit behind. And so these terms always show up with 1 over S. And this term on the induction motor, actually, if you go through the derivation, it's really 2 terms. It's the rotor resistance itself plus 1 minus S. So when S is 0, that means the induction motor is at exactly the synchronous speed. And when S is 1, it means that the rotor is stationary. It's just locked and stopped. So if you look at this resistance, when S is 0, then I get 1 divided by 0, which is infinite, which means that this impedance is infinite, which means that the induction motor has no power at all. So an induction motor will never be at exactly synchronous speed unless it has no power coming out of it at all. Similarly, if the rotor is locked, that's at 1, then I get 1 I get 0 divided by 1. And so this resistance goes to 0, and that means that, you know, the power that's coming into this part of this circuit represents the power being consumed by the load, so it goes to 0. So if it's locked, you're at 0. It's not spinning, so clearly it's not providing any power. Or if it's at exactly synchronous speed, it's also not providing any power. So this circuit can be useful for kind of talking through how induction machines work. There's other terms in the equations for induction machines that look very similar to a synchronous machine. So instead of doing, well, S is kind of like delta omega, actually. So S is, well, officially it's the speed of the rotor minus, depends how, I always forget the sign on it, versus, you know, synchronous speed. So it's kind of like the deviation in speed, so it's sort of like the omega term we had on synchronous speed, where we meant that being the deviation from synchronous speed. And so this equation is very much like the synchronous machine, where you're just saying the change in the speed of the motor, we have the 1/2H again, and then the mechanical torque minus the electrical torque. So just like the synchronous machine was. There are then, again, I'm going to kind of skip through this, but you end up getting the same types of X and X prime and X double prime and the leakage reactance. The math for a synchronous machine is similar to an induction machine. So this equation right here is representing the interface between the network and the induction motor, and this is representing all the flux dynamics for the machine. We're going to get to looking at how this stuff affects things here in a second. Let me just jump ahead to the circuit, because that's where I kind of am most familiar. All right, so the final circuit, after you go through all this stuff for an induction machine, ends up looking like this. And if you look at it, it's similar to the synchronous machine. So the synchronous machine that we derived in great detail yesterday is right here. And this is the double cage induction motor, and all the parts of the model that I do not have highlighted are identical to each other. So what is different is there are some cross terms between them that are caused because the rotor is not spinning at synchronous speed. Whereas on a synchronous machine, it is at synchronous speed. So these terms do not exist in the synchronous machine world. The other thing that's not there is the round rotor, or the synchronous machine, had a field voltage coming into it. On an induction motor, the field is just shorted out. They call it a squirrel cage. Why do they call it a squirrel cage? Because it looks...
So you got two end rings.
Okay.
Around the shaft, and then you've got a bunch of bars that connect the end.
Okay, so literally if you look at it, it looks like a cage you put a squirrel in.
But if you took the copper bars out of the cage.
Okay. Yeah, well, back in 1890, they probably did put squirrels in cages.
Well, it sounds better than squirrel spinning wheel, than squirrel running wheel or something.
The advantage of having actually seen such a device. So the slip terms aren't there, and there's no field. So
Hamster wheel. What they call hamster wheel.
all right, so as you tweak, if you plot the real power as a function of speed, you get something like this, where as the speed increases, it goes up, and then eventually comes back down, and at exactly 1 per unit speed, you don't have any power at all. So for the most part, a synchronous or an induction motor is going to operate right in here on this sort of nice linear area of the machine. When you start operating over here, We're gonna talk about that in a second, but that's, you're stalling, you're slowing down. What happens when you slow down is the power starts going up for a while, then drops off, but the reactive power goes way up. And we'll see that in some simulations I run up here in just a moment. All right, so this is all talking about the electrical part of this thing. So the electrical power, it's in here. The electrical power on the synchronous or on the induction motor ends up being, just voltage times current terms. Not surprising. But then the question is, what is this mechanical power? So one of the phrases that John Undrell has pounded in people's heads is that an induction motor is not a load. It's a device that turns electrical energy into a mechanical torque that can then actually run a load. So the question is, what is that thing that the induction motor is connected to? And we don't really model that thing in great detail. We basically just give a function that says how much torque is that thing asking for as a function of how fast is it spinning. So is it a fan? Is it a compressor on an air conditioner? Is it a compressor on, a nail gun? I don't know. It's like, what is that thing that's being run? And that is the actual load, the thing doing the work. And so we model that as give me torque as a function of speed of the rotor, and that's it. And most motor models you will see are not that complicated. They just give you an exponent, and that's it. Now, there are some, let me just kind of peek at one here. So this is Sim 5, which is so this one is just doing an exponent. So torque is some nominal torque times speed to the power of d. But there are some models that are more complicated, or they just have more terms. But again, it's up to the person designing the model to tell you what is the mechanical torque. So if someone puts a 0 for the exponent here, then it means that the torque is constant, which I think Dimitri would know more than I. That's a compressor, tends to be. If it's a fan, think about a fan. The faster it spins, it's got a big inertia because it has big blades. It's going to take more and more torque as the speed increases, and I believe it ends up being the square. So if it's running you're in a manufacturing plant and you've got giant fans trying to pull air out of some industrial process, then you'll have a motor load where the exponent's 2. Now, as a user of Power World, mostly you're just going to say, okay. You're not giving those models. You're given those models, not making them. But that's where these terms are coming from. And one thing to remember is that's the torque. So that means that the power, actually that should say +1. That's a typo. Because the power is torque times speed. Except there's a problem with the model. I might have time to talk about later, but anyway, the power should be the torque times speed. All right, different induction motors are going to have different characteristics for these speed versus or torque versus speed curves. I think they call these NEMA classes. I don't even know what NEMA stands for. National Electric Motor Association. Yeah. So they have different kinds of motors. So if you want a fan motor is like this, why? To make it easier to start?
Yeah, usually it's starting performance.
It provides a lot of torque. Yeah.
Yeah. They have low loads at starting torque, but high loads at speed. So they instrument them in various ways.
Yeah, so basically if you build the induction motor by kind of creating the inductance and resistance of the machine in the construction process, you can affect what this looks like.
Yeah, most mostly it's the shape and resistance of the rotor parts.
Okay. And then B is similar to A, but just down. And then the C values are the compressor motors. I'm guessing that's because as the speed drops on a compressor, you want the power to stay up as long as you can, because shutting off a compressor, you gotta wait a while before you turn it back on.
I don't know, it's
That's
starting torque is usually the issue.
Yeah, so it's
So
much
higher
flatter.
starting torque.
Yeah. And then finally, like, okay, you're right, so this is like a very high starting torque. So that'd be like for a hoist, makes sense. When you first start picking it up, you need a lot of torque to get it started. So anyway, another whole class of engineers designs those, and all the different characteristics of the machine themselves. So the point is, there is a torque up here. Starting is down here at 0 speed, so the amount of torque you can get is dependent on this curve. Another thing that happens is when there's a fault, this characteristic actually just sort of goes down. So you get less and less electrical torque out. And so during a fault, the mechanical torque could be higher than the maximum electrical torque, which means it's just going to keep slowing down and eventually stop. And that is what is called stalling. So let me just, I have an example I kind of put together here to demonstrate this. So this is a little case that Tom had put together just half an hour ago. I went in and I went to stability here and I inserted, it would go to insert and then you pick one of the load models. And I picked Sim 5. It's actually a PSSE model, but there are similar ones. And I've got it set up so that it's 100 MVA base, and I just took all the default parameters here, and the exponent is a 1, so it's not a constant torque, it's a linear torque. And now I'm going to run a simulation where I fault the bus. So I've told it that at 1 second I want to fault the terminal of that load, and then I messed around with the clearing time until it just barely recovers. So it's a 21 cycle fault. That's bad. But in this example, it makes it a nice presentation of it. So if I hit run here, it's going to run through that, and what I want to show you is, first of all, here is the voltage. Actually, that's the speed. I want to do the voltage first. So here's the voltage at the terminal of that bus, and what you see is it faults, goes to 0, clears the fault, and then it actually takes a little while to come back up. If we look at the motor speed, as soon as the fault happens, the voltage drops way down. If I were to, I think I can actually plot this. Let me just do that. I go to load. I can plot the mechanical torque and the electrical torque. And so the electrical torque goes to 0 during the fault because the voltage is going to 0, and basically that torque speed curve just flattens out because there's no voltage at all. And so if you look at the mechanical torque, the speed of the motor starts slowing down. Because I said that it's torque, the mechanical torque is a function of speed, then it does start dropping. But clearly there's a big mismatch between them. And then the fault clears, and then you get a huge spike up in the electrical torque because it's trying to speed back up. It's trying to unstall itself or prevent itself from stalling. So what does that look like for the speed? The speed goes down, fault clears, and then it starts going back up. And then the interesting thing that we care about is, well, what does the load look like during this? So the load started out as 100 megawatts and 34 bars, or 35 bars. In order to re-accelerate itself, the red is the bars and the blue is the megawatts. You end up having a big spike in power in order to accelerate yourself back up and then settle back out to a new steady state. And at some point, if that fault happens for too long, like let's say I made it half a second, yeah, things are going badly. Actually, one of the generators tripped during this simulation. Why don't I prevent that? Yeah, so there I prevented the generators from tripping, which caused the whole system to just go unstable. So basically what happened was the electrical torque just never got up high enough to to bring the speed back up, and it just kind of went unstable.
So when it goes unstable like that, that's not actually what it does, it's just numerical.
I suspect this is what it would do, but I just turned off all the protection systems. Everything would have tripped at this point. And if I look at the, yeah, I would have to. I mean, you have a power oscillation going, very big, so something would trip it. Numerically, this isn't just numerical noise. This is what the equations would do. But the protection system would trip.
Wouldn't allow it.
No. Yeah, and this is what this is getting at. So one of the things I could do on this is one of the parameters of a lot of these induction motor models is there's a parameter here that says if the voltage falls below some threshold for longer than a certain number of cycles, then trip. So if I were to change that, I think I'd actually get that to trip, which might prevent the system from. Yep. System goes okay because it just trips the load. Because the voltage dropped too low. So yeah, it's again, at some point you have to model the things that would protect things. All right, this then goes to tomorrow I'll talk about transient limit monitors and the WEC finger diagram. You guys have been around long enough to hear that term. It came about in WEC first because you guys actually started modeling induction motors after the 1996 blackout. You had what you called the interim load model, which was around for about 20 years. But it was an improvement because it was including some of this behavior that when a fault happened, the voltage would drop and the system doesn't recover right away. If I model, let me just do this because if I switch this load to a constant impedance model instead, if I just disable it, it'll work. The simulation's not nearly as interesting. No. The synchronous generators are actually having trouble. So if you go back to this is modeled with a constant, I think it's constant current, constant impedance. constant current, power, constant impedance Q. It recovers very, very quickly because I'm not modeling the dynamics of the induction motor slowing down. Fault clears and it has to speed back up. As soon as the fault clears on a zipped model, the load just whoop, bumps right back up because the voltage recovers so quickly. I mean, look at this. It goes here. It's like recovers about a third of the power instantly on it. And so up until you guys started modeling motors, I'm going to guess that you didn't even have this diagram. I'm guessing. Did you?
Oh, yeah, that thing.
You did have it? Okay.
Yeah, we'll look at it.
But I'm guessing it morphed. You had to change it a little bit. And then when you added the composite load model, we had to change it again because you're modeling more and more the behavior of the load, so you're seeing more dynamics in the voltage recovery. So. Should I go through what this means, or has everybody in this room heard that 100 times? I think I'll go through it, because I'm going to guess a third of the younger engineers they've heard finger diagram, but they never really knew what it meant. So what this is showing you is the voltage magnitude as it progresses over time. So something happens and the fault happens. The fault clears. We don't really care what the voltage is during the fault, because clearly it's bad. So your criteria is telling you what happens after the protection system happens. What are the rules for how I have to recover? So after that, the voltage spins around a while, and what your rules will say are something like, if it drops below this level here for more than some period of time, so it goes below this level for more than that time, then I consider that a violation and I have to fix it. And fix it means I have to build a new line, I have to put in an SBC. Honestly, if I was you, I'd be happy when that happens. It means you get to do interesting work. Or you have to do interesting work, I guess. So that's what these are. And simulator calls these transient limit monitors. You can define these things. We'll talk about those tomorrow a little bit. All right, another thing you can do with motors that's kind of fun. You don't usually do this in your kinds of studies, but you can actually start the load off and then close it in and watch it start. So in this case that I set up, I have this load here again. And I have it configured so that it's that it's open right now, and it has a Sim5. Because it's open right now, it's important, this T-nom parameter on these things, usually you don't even need to give us that because we calculate it based on the initial condition of the load. We calculate what, if you go back, the mechanical torque is equal to some nominal torque times the speed to the factor of D. When we initialize the motor, we calculate what its speed is. So, if it's 0.95, let's say it's a fan and it's squared. We know the initial power, let's say it's 100 megawatts, divided by torque. Power is torque times speed, so torque is power divided by speed. So we divide it by 0.95 to get the initial torque. And we will calculate this nominal value based on the initial condition. But in the situation where it's open, it's not energized, that's when I need the T-nom in the software. So I have it set to 1 per unit based on a 100 MVA base. So if I run this now, I'm going to set up a little simulation where I run, my event is I close that load in. So at 1 second, I close the load in the simulation, and we can actually watch it start up the load. So what happens is the load starts at, I'll just kind of zoom in on it, starts at 0, At 1 second, we close the load in. It takes a while. It's actually quite high for a while. Sorry, that's the bars. This is the power as it's going up. So it's speeding up. It goes way up, and then it comes and settles back down. So it's a very common looking startup torque. So when you hear the word startup torque, that's pretty high that it goes up initially and then gets itself running and settles out. Later tomorrow, I'm going to talk a whole bunch about how we actually do numerical integration. And one of the interesting things is right in here is really, really fast dynamics. I'm going to run this at instead of a quarter cycle, I'm going to run it at a 40th of a cycle again, just so I can really show you what's going on in there. There's some really high frequency dynamics when you first get started up on an induction motor. And just remember that, so tomorrow when I talk about some tricks in the numerical integration, we'll come back to that. There's something we call multi-rate integration. I think Power World we tend to call it sub-interval, but I'll talk about that tomorrow again. All right, the need for better load models. Induction motors were good. Kind of the history of them. It's up until the 90s, you guys just use zip models. I mean, up until 2015, probably 2020, the East still uses zip models. But because of an outage, the 96 outage was partly caused because you figured out that you needed to model your loads better. And so that created the Motor W model that you had used for a long time, and then moved into having to model other things where you had events. Have you guys had these events in the Northwest, or is it more Phoenix, Florida? Yeah, folks in the South would see results like this, and look at this time scale. This is 30 seconds. An induction motor doesn't do this. Just a big three-phase induction motor. So there's a fault, the voltage drops down and then just kind of hangs out somewhere between 0.6 and 0.8 per unit for tens of seconds, and then eventually recovers. It actually usually recovers high at the end. And this led to what's called the single-phase air conditioner model, which I want to kind of walk through because it is the model inside the composite load model that allows you to model this behavior, but it's also the one that gives you really weird results and customers don't understand why. So kind of want to walk through what this thing is doing. So LD one pack load one phase air conditioner is what it stands for. It's inside the composite load model that you guys are used to using. It is not intended to represent one air conditioner. It's meant to represent thousands of air conditioners in aggregate. All of these models are like that. So we're not modeling, frankly, any of the dynamics of the actual device itself. We're just modeling the general behavior of it and how it trips. And it trips in 3 different ways, so it's kind of complicated. So, yeah, I mean, I always think it's not like if we gave you the ability to model 1,000 separate air conditioners on each feeder, you would even be able to give us the data to do that. So there's kind of no point in making a model that was even better, I guess. So the way the model was created is in this building. And also, who else did the tests? EPRI and Edison. Okay. They did testing where they would fault. I assume you guys went to Home Depot and just bought some air conditioners. Hooked them up in the lab, and they would fault them for a certain amount of time. They would run them at different voltages and just kind of looked at what if I put this voltages in and wait about 10 seconds? What does the steady state behavior of this device look like? And then also running different durations of faults, figuring out when does it trip. And then I suspect they went through figuring out, they found out when it tripped, but then they realized there's lots of different reasons that it trips. So those are all going to show up because there are 3 different ways this thing can trip itself. And then they also figured out that these motors do stall, but they're really small. From the pictures I've seen, I'm going to guess the motors are about this big. Yeah, but is this about how big they are? The smaller? Bigger? So maybe the coffee mug? Yeah, so they're little, tiny, they're induction motors, but there's not a lot of inertia there. So when they start slowing down, what they figured out is they tend to stall very quickly. If they stall, they do it really quickly in such a time frame that we can't really model the dynamics of that. Maybe we can. We're still looking at that. But we need some transition of when does it stall and when does it not. And so, yeah, before I come back to that. So what they figured out is they plotted these with different voltages. They would slowly drop the voltage on the induction, on the air conditioner. And what they would see is there's kind of a little bit of a slope and change in slope here, and they'd start dropping it more and more and more and more. And at some point, it would stop following that, and then it would start going back down this green curve. And then, depending how long they applied the fault, it might go down here, but if the fault cleared in, say, 5 milliseconds, then when the voltage recovered, it would just go right back up and it would stay in this highlighted green. So in the model itself, we call this yellow highlighted area the operating curve. The operating curve has 3 different parts to it. There's one part that's an impedance. There's another part that is this curve right here. And then there's another part here that's the purple curve. I think most of the time this purple curve out here is just flat. However, if you faulted it long enough and at a low enough voltage, then the motor would stall and it would just stay stalled. Meaning by stalled, it literally means it's just sitting there and not spinning. And at that point, it just looks like an impedance. And it's just sitting there, not spinning. Suddenly the voltage recovers. It doesn't restart. It's just sitting there. It's now acting like an impedance. This is bad. When the voltage recovers, the power is going to go way high. Oftentimes somewhere around 3 to 4 times higher than where it was operating initially. And it's just going to sit there until it burns something and something trips. And that comes back to these thermal relays. So what Steve and Dimitri and folks at EPRI and Bernie Lesure at Wisconsin doing all these tests figured out is some motors restart and some motors don't. Have you ever figured out why? Does it depend on the scroll versus not scroll? Depends on the technology of the compressor. But I don't want to go into that here. But there's different ways of physically making the compressor, some of which can easily restart and some of which have to wait 20 minutes before they'll restart. So if they have to wait 20 minutes, for our purposes, they just never restart. So the model that they came up with then is these performance curves that I just described are these shapes. This is the one for power, but there's a similar one for reactive power. And then those are modeled right here. All the rest of this block diagram right here is how do I trip the thing? And the model is not meant for one. It's like I've got thousands of these things. So what percentage of them will trip? So there is a function up here called the contactor. That's one way of it tripping. So I don't think I have that picture. All right, the contactor model is just a model that says as the voltage drops, this is the percentage of the motors that will continue to operate. And there will be a point at which the voltage has gone low enough that they start tripping. And they'll go down, and then eventually they'll go to zero at some other voltage. And this is, ideally you'd go test 1 million air conditioners, but that costs too much. So they probably tested 50 instead. Is that about right? To kind of come up with what does this look like. As the voltage recovers on this, there's a device, there'll be a voltage at which they'll start reconnecting and they'll go back up. And in practice, the voltage might go back up and then suddenly start going back down again. And so then we'll go back across here and back down. So in practice, it's kind of following a curve that's something like this, depending on how you've recovered or not. That's how this, it's kind of like a hysteresis curve in there. So that's modeling a device. And Dimitri, you're not usually in the room for me to ask. This is the ice cube thingy, right? It's just like a little under voltage relay that's tripping things temporarily and letting them come back.
The would also be the contactors. You have a DC power contactors. So you use a supply to the control circuit to use the open the contactor.
Okay. So if the voltage drops low enough, it just opens, but it'll try again every so many seconds to come back.
It's a spring, right? So once you have enough voltage in it, it's spring. So you have enough power to overcome the spring tension.
Okay. So if voltage drops, the spring falls off and comes back. Then you got to overcome that. Again, that's why there's a separation in it. Okay. So that is one method of tripping, and that's modeled right here. Another method of tripping is there's probably some under voltage protection on some of these air conditioners. So there's a part of the model that says if the voltage falls below this level for this amount of time, then trip 30%. So the model itself, if I go back here, it'll have input parameters that are right here that are saying that trip this fraction of the motors if the voltage drops below here for this amount of time or here for this amount of time. And these, once you trip these, they never come back. Again, remember, if you go out to one air conditioner, you're not going to find all these things. This is like just across a family of air conditioners. All right, and then finally we get over to the part that's more complicated. So right here, it's like we split the motor, we split this load up into two pieces. And the two pieces are, motor A is motors that once they stall, will never restart. Stalling and restarting are, I wasn't around to argue about nomenclature, so I can nitpick now. But by using the word stall and restart, it sort of implies that we're simulating the speed of the motor and actually the flux and dynamics of it. We're not. When we say stall, we literally just mean jump from here to here. And we say restart, we mean jump from here to here. There's no speed. If you go look at this model, there's no rotor speed. We're not modeling it. So when we say stall, it just means it gets stuck on this green curve and will never come off it. And the B motors are the same motors, except when they stall, there are some restart parameters, and they are right here that say what fraction of the motors after they have stalled will restart, and how high does the voltage have to go and for how long before they restart. So that's what those parameters are for there. They're just how to jump back and forth between those curves. So if you think about the A models, I just said they're going to stall. They're going to stay stalled forever. So we have to trip them somehow. And the way we trip them actually, I guess we don't really show it that much in here. We are you're just integrating the current. So right here, we're going to calculate the current squared times the resistance. Times the stalling resistance. So we're going to say I squared R, those are losses that are heating up the motor. And we're going to integrate those losses over time. And there's a time constant in here that is the heating time constant. And then this is telling you when they start tripping and when they finish tripping, so that eventually they trip out. This time constant is quite long. It's usually like 15 seconds. And it's what gives you this behavior. The reason it gives you this behavior with this load, voltage drops, these motors stall. They're now on that green curve. The voltage recovers, but because they're on that green curve, their loads went way up. So even though the fault is gone, the load at these particular motors just went up by a factor of 3 or 4. And therefore, the voltage stays depressed, hangs out there for somewhere around 15 to 25 seconds, and then the thermal relays finally start tripping them offline, and that's what gives you this response. So I have a picture here.
And then the other fraction goes back to the...
Correct. The other fraction, as the voltage recovers, it might go up high enough that it'll pop back down here and the load will come back. Exactly. So this is actually, yeah, this was in the Phoenix area. These are the kinds of curves that you get. This was a test that the customer was doing, and they were like, "What's going on?" And I was like, "That's exactly what that motor's supposed to do." But it's kind of weird. So they ran a fault. This is a plot of every load bus voltage in SRP, Tucson, Southern California, Edison, and APS. You can see the voltages are around 0.6 to 0.8 in here, just kind of hanging out. And they just sit there until about 15 seconds. And then the thermal relays finally start tripping them. And then typically the voltages all go way high at the end because we just tripped a whole bunch of load. So this is one of those situations where maybe we need to model the capacitor banks that would trip off to bring the voltage down. Maybe even tap changing transformers might be useful to get rid of these voltage overshoots of 1.2, 1.3 per unit are not unusual. But you have to run it out to 25 seconds or so. And so yeah, here's the kind of classic response. Here is this is a good picture. This is showing the megavar loads in those areas. And they start out here, and in particular, look at SRP. Starts at 500. The megavar loads go up to 6,000. Hang out there for 15 seconds, and then eventually come back down to minus 1,500 because a whole bunch of loads tripped. So this is the kind of behavior that you'll see with this model. Many of you in this room haven't run simulations for 30 years, but for folks who have never used this model before and they see results like this, their first assumption is to call me or whatever software vendor and say, why is the simulation wrong? Because it is very different, but this is the behavior it's supposed to So these are some good documents. Again, Steve and Dimitri and Bernie are the ones that I've talked to the most. Lawrence Berkeley has funded a lot of this work and has some good links on here. One comment about stalling. I skipped over the two most important parameters on this thing. Where are they at? No, so in this model, there's a V stall and a T stall. And all that was done with this model to start was to say it will stall if the voltage drops below this value for this amount of time. And the initial testing that folks did here in this building, let me hide this. Just look at this to start. So in about 2012, they're testing where this is, it's hard to see here, but this is voltage. No, sorry, this is time. Time versus voltage. So they would run a test where they were actually looking at the three-phase waveform, and they would fault it either at the peak, somewhere in the middle, or at a zero crossing. So they'd actually set up their thing so they'd apply the fault exactly at a particular point on the wave. And so it would actually go to zero instantly and then recover instantly. And what Steve found in the lab was, depending on whether he's faulted at the peak or the zero crossing, he got very different results as to whether it stalled or not. So this says that at 3 cycles below 0.45 per unit, it will stall. But if I can't remember which one's zero crossing and which one's a peak. I assume peak's worse. Zero crossing's worse? Okay. So up here, this says for a zero crossing, if I fault for 3 cycles at 0.62 or so per unit, it will stall. So we actually got different values for this. So the initial release into the wild of the composite load model in 2012, people put V stall of, I think it was 0.6, is that right? And T stall was 3 cycles, 2 cycles. And that got released into the WEC environment. The first 10 companies that used it ran it and got rampant FIDVR events all over the system everywhere. There was much yelling and screaming at WEC meetings for a long time because they were like, we don't see that in real life. Dimitri and Steve were probably going, oops, what's going on? But like anything, you can't fix a model until someone starts using it. And they went back to the lab, and they're like, okay, well, clearly there's not this much stalling of air conditioners going on. They were using the conservative curve here. And so, I don't know, whose idea was it to do this? John's and Bernie's. They were like, well, you know what, in real life, a fault doesn't happen instantly. You know, the fault doesn't happen at your house. It happens out in the power system somewhere, and then the voltage drops. It probably isn't going to drop faster than about 1 cycle. So they went back in the lab, and instead of applying the fault instantly, they ramped it down over the course of 1 cycle. And then, checked, when I apply the fault, is it at the peak, is it at the zero, where, does it matter? And they did the exact same set of curves, and they all looked kind of the same. And so what it was telling them is, oops, we shouldn't have been using this red curve, which had that stall voltage too high. We should have been using something like the red, or we should be using something more like, is it 0.45 now? So they dropped that. Which basically, I mean, what was happening when it was 0.6 is if you applied a fault somewhere, you'd have hundreds and hundreds of loads that would have their air conditioner stall because the voltage drops that low in quite a big area. But when you make the voltage lower, maybe you get a couple dozen loads instead of hundreds. So you don't get, I suspect this curve was run with the 0.45 value because I just did it a couple months ago. I suspect if I ran this with the 0.6, this might have gone up to like 20,000 bars and the system would have just collapsed. And SRP would have been like, okay, we need to go spend $100 million on new transmission lines and SVCs, and their bosses would have been like, what? You just changed the software, why should I? So, but in this case, I think this was okay. I'm not sure. So anyway, that changed to this, so that they're using this curve now, really this point. And the problem with this is, what happens if the voltage drops to 0.46 per unit for 2 hours? If we're using this, it will not stall. If it drops to 0.45 for 0.0334 seconds, it will stall. So this is a little bit crude. So one of the features that's in later, more recent versions of simulator as well as GE, I don't know if PSSC's put it in or not yet, but there's this sort of super secret thing that if you put in a negative value, it's not secret, it's in our help. It's way down at the bottom and most people don't read it. So it's saying here that if you put in a negative value for V stall, is it saying that there?
Yeah, if however V stall value entered has a negative.
Oh, there it
number.
is. I should make that in red text. If it's entered as a negative number, then we put in this, we kind of integrate a state so that if it's stalled if it drops below this value for 15 cycles, then it'll still stall. There's kind of a different set of, there's a piecewise linear curve. Again, I go back, it's like the answer to most problems now are just put in a piecewise linear curve of how it stalls. So I don't know that anybody's doing that yet. You guys playing with it, Dimitri, but none of the WEC cases have that yet.
We make our own data set.
Correct. All right, so then that led to the composite load models. All right, composite load models are what you are used to, where you have, this is what's in your power system case. You've got just a transmission bus and a load, and then you got this thing called CMPLD-W that you've never looked at and somebody just handed to you. So what is it doing? Inside this, at least, I can tell you what it does in Power World. In Power World, when we run transient stability, the moment you hit initialize, we actually make a copy of the power system and then start messing with it. One of the things we mess with is if you've got a composite load model in there, we're going to put in a distribution equivalent. That's part of that model. So we're going to add 2 buses to your system. We're going to calculate the tap here. We're going to calculate the impedances here from the input data that's in that model. We're going to calculate what the P and Q that actually gets down to the end of this feeder is. And then we're going to chop that up into a bunch of pieces or components, thus composite components. And for your model, in practice you have 3 induction motors, 1 air conditioner model, a static model, and an electronic load model. All right. I'll get to some other stuff here in a second. One comment about the induction motor models. you guys have distributed generation yet? Let me rephrase. Are you actually modeling the distributed gen that you have? You're starting to
Some.
do it? Okay.
Yes, some.
Okay.
Yeah, otherwise it's netted in the load. So at WEC, there's a huge push to break out the DER
Correct.
or DER.
Dirt. So inside the load record now, there are three, this isn't a power flow. There are three extra input parameters of how much distributed gen megawatt, distributed gen megavar, and you can actually open or close just this little piece of it. And so what you would do is if I had a let's pretend we're in Phoenix where they have a lot of this. If I got a load sitting here, maybe historically this was a 100 megawatt load. And over the last 20 years, the homes that are down here that we're not modeling have started putting solar panels all over their roofs. And the load has also gone up over time. And maybe the net load that I'm seeing right now is, say, 110 megawatts. But I don't know how do they just send out surveys? They're not going house to house. How do they know how much distribute? I guess they have the meter data. So anyway, eventually, somebody like Southern Cal Edison or SRP would figure out that at this feeder, there's actually 30 megawatts of solar, of PV down there.
Well, because they're the distribution provider also, and so they're providing credits to those homes.
So they know.
So they know what homes, or at least at what interconnection, like, points.
Yeah, the difficulty is, do they have those homes mapped to feeders?
Yeah, and that's what I'm saying. I think they do.
Okay.
Really,
In theory.
the ISO does.
Yeah, so
They're pushing for it.
yeah, so what's going on if the net load that you're measuring here is 110, then the load itself is 100 that would be the megawatt. So in simulator, there would be a megawatt value for the load. And then there's a distributed megawatt, and then there's a net megawatt. So the net megawatt here is 140 minus 30, so 110. So in the power flow realm, this is just bookkeeping. I mean, all we're doing is we're giving Lucas somewhere to come in here, and instead of just netting all this out and basically putting in what the maximum feeder value is over the course of a year, he's figuring out that he knows there's a certain amount of distributed gen there, so he'll add that here, and then he needs to add that to the load, essentially. And then
We'll subtract.
well, but the net will subtract.
Okay. Oh.
Yeah. So like if you knew the net was 110, and then later you go, oh, I know there's 30 megawatts of distributed gen there, you would need to go in and change the load to 140 and the distributed gen to 30. And then the net would remain 110. So this value still refers to the load. And this value is the distributed gen. And then there's another value that just says the net. Or you notice the net is not blue, you can't edit it, because we're just doing the subtraction for you. Subtract. Does that make sense?
Yeah.
Yeah. So that's in the power flow.
Is that, can I ask a question?
Mhm.
Is for APS or whoever's doing this, so initially some of the solar stuff that would make its way into wet cases, you'd get a light summer case, which is 4 in the morning, had solar on. You're like, well, you can't do that. Solar's not on at 4 in the morning, so let's pluck all that. So it was a very manual thing that some people, is this also very manual? So there's long ID stuff in here, but if you choose to put DER in this thing, you have to remember, oh my God, it's the wrong case. I need to go in there and run an aux valve and pull that stuff out.
Well, that's
Turn it
why,
off.
like, for instance, we're not running our DER in the load. We would rather have it on the bus.
Okay.
Okay, and I'll get to a second where that's a problem with the transient.
I don't run transient.
Yeah, I know. Just-
And Jamie, we can go longer because
Okay.
I'll struggle for filling up my time unless we want to
Okay.
break and then we can come back after the break and keep going.
Why don't we do that? Why don't we take, because I'm kind of at a breaking point, we're going to talk about how this gets split up and transient. So let's take a 10-minute break, start back up.
Because Lucas,
That'll be good.